Okay. Well, I'll get. This is for the next. Thanks very much, Rick, for the invite and giving me the opportunity to talk about basically, well, the past 10 years of playing with UAVs and geophysics, and I'm going to try to convey over the next 15 slides, well, as much as I can of those 10 years, and the good, the bad, and the ugly, and what can be done, and what is its place in the toolbox for exploration. That tells you the same thing than any others, that our attorney have been trying to convince me for the past 20 years that whatever says is word of fiction. So we'll move on about that. I'm a geophysicist by training, but I've been doing a PhD in geology also, but I never traded or practiced as a geologist. I turned to the dark force very quickly and spent the past 25 years in airborne geophysics, from a traditional airborne geophysics and down to, well, basically light platform and now UAVs. And 10 years ago, when I left the traditional airborne geophysics, we've been looking at, well, what is the next step in airborne geophysics? And that was the origin of the program we call FLY. We identified a platform, a very light aircraft, which I'm going to talk about today, but there's been also works the past 10 years. Today I'm going to talk about a UAV that was the second identified carrier or vehicles which we could use for geophysics. And you have in that slide a table with a couple of commodities here and also a specific application. And here are the four main geophysical technologies you have in a toolbox. And in green, very specific applications for most of the commodities or applications, and the plus minus is just showing you roughly if it helps or not. That was just for a summary, and I wanted to use that to show you all what are the technology UAV suitable. Now, obviously, the magnetics is the most mature now. The gamma spectrometry is also available. And I would say yes-ish, because you see we have some limitation here in terms of payload, but I'll get back to it. But magnetic and gamma can be flyable. EM is, from an engineering perspective, also ready, and I will introduce something quickly from a manufacturer in Canada. Gravity, there's some way to go, but there's some works happening, and I'll touch base onto that also. And all of that was basically for technologies which are on a less than 10 kilo payloads, which is easy for UAVs that are mature enough now in the industry to be used for that. And first, I'm going to try to go through a certain number of considerations and over myths and perceptions and a lot of stories. So we're going to spend some time on that slide. The first one, I usually don't use the term drone, which is more of a military, and it creates a lot of perceptions, and a big problem in our capabilities on using UAVs in a civilian application. There's a bad publicity, it's a bad acceptance by the public about that. So usually I try not to use drone. Now, you've heard the term UAVs, unmanned aerial or airborne vehicles, and that basically it's a vehicle itself. It's a carrier. Frequently, that vehicles cannot fly on its own. It needs a ground-based stations, and it needs also a management software system. And all of them together, it's what we call a UAS, or in a previous presentation, we've been talking about the RPAS, the RPAS. So just a bit of a semantic, but it's important to understand a UAV on its own, well, it's a vehicle. And just like your human carrier, if you do ground geophysics, or a donkey, if you have to use a donkey to do surveys in Africa, for example. Some myths and perceptions I heard over the past 10 years is that, well, it costs less to buy, to fly, to operate, to land, and to dispose than a piloted plane. Okay, it costs definitely less. Let's say a UAV can cost you anything from $15,000 to $150,000. It's a lot less than $1.5 million. But it's also a lot less mature. And when it comes to cost of operations, cost of maintenance, some UAVs, and particularly the one on steroid, which will cost you 60 or 100,000 euros, I can tell you it costs more than maintaining an helicopter. And that's our experience. So you need to be careful about these statements. Yes, they are cheaper at buying, but some of them are just way too expensive to operate. And then you have to also look at the balance between affordable and cheap. When I say that is that frequently we hear it's small, so it's easy, it's cheap, and that is a very big bullshit. We just lost a lot of money when we started 10 years ago, and that's something you need to keep in mind. It's not necessarily cheap, and because it's also not a fully mature technology yet in terms of operations. Something else also frequently here that UAV are going to replace the traditional manned aircraft in exploration. Now that's not going to happen, and then I think, yes, I put that slide here. On that slide, on the horizontal axis, you have a maximum endurance. On the vertical is a service ceiling. Yes, all the UAVs can go way beyond the manned aircraft, but we are limited. Your space in terms of civilian application is limited by the civil aviation regulations. You cannot go there. And actually, the UAV in an exploration toolbox or the exploration operations is here. So a UAV is not here to replace the airborne traditional platform, but is here to replace a part of the ground operations and slightly overlap towards what an helicopter does. And this is its window. And why I insist on that is that if we can focus on that, we will help tremendously in allowing the UAV to take its, I think, righteous place in the toolbox. Because right now, it has a lot of potential and a lot of advantages, but it's not yet fully accepted and not yet delivering on its value. Sorry. Some aspects of constraint and restrictions. Let's talk about the effective surface on a UAV. I have some clients coming to us and says, look, I have a 100 kilometer by 50 kilometer survey block. I want a UAV survey. And I says, forget about it. I'm not doing it. An effective surface for a UAV, most of UAVs, and with a certain set of operations, it's 4 by 4 kilometer. Anything beyond that, you're going to lose money. And that's from a contractor providing the service or versus any mining company who wants to do the survey on their own. It means that your 4 by 4 kilometer, okay, I'll get back to that later. The second one is basically what you heard about is most of us regulations will limit the operation to loss, line of sight. And line of sight means that basically your UAV cannot go further away than what your pilot can see. And that in general is 350 meters, 400 meters. So if you remember your 4 by 4 kilometer effective surface and your UAV cannot go further away from your pilot or the ground-based station at 400 meters, this means you have to cut your 4 by 4 kilometer survey area in sub-blocks, which are 400 by 400, for example. And then you have to move from point to point to be able to respect the regulation. And that, obviously, it's a big constraint imposed by CAA, and I'm not going to argue on that. It's necessary in many aspects. It's a big limitation on what the UAV can do. Of course, slowly we see the beyond line of sight options happening. It's usually still an exemption. You need to apply for it, and it's very specific conditions. It's very difficult. Europe is pushing in that sense, and there's a partner based in France there as we fly BLOS already, and it's obviously opening a large window of operations for better results. Another big constraint you will have when you want to do a UAV survey is what we call a REOC and a REPL. A REOC stands for Remote Operation Certificate, and REPL is your remote pilot license, basically from their respective countries. They cannot fly in Australia. They will need a local pilot license. And the second one, you need to operate with a local operating certificate. Now that obviously, the point is, when you want to run a service, you need to be aware that many contractors outside of a country where you are or where you need to go will have to face this regulation problem. And it's not sorted over a month. We've been there before, and I'll get back to it during a survey, during a next slides. And the next point of constraint is UAV autonomy. Now, we all immediately always want, I want one who wants 10 hours autonomy, and it's not necessarily your best solution. Actually, you need to balance what the limited flight time or travel distance versus how long you can stay in the air. Now, when you have a limitation with a line of sight, whilst being able to stay in the air for 10 hours doesn't really mean much because you're limited to 400 by 400 meters before you need to move to the next spot. So you have to be careful about autonomies. An autonomy right now, 5 minutes is ridiculous. An autonomy of 45 minutes is nice to have, but it's not necessarily the most effective in terms of operations. Something at 20, 25 minutes, from my experience, is very good within the present state of CAA regulation. And then again, a couple of challenge, but I'm not going to spend too much time because I'll go through it with certain of the slides. But one important one is the last one, which we always forget about it when it comes to UAV. But unless you manage to train an octopus to use joystick, you're still going to need a UAV pilot to fly a UAV. And that I'll come back to it later in terms of what is the future of a UAV. We'll have to work on removing that pilot or whoever is flying that UAV, and including the octopus anyway. That's a bit of a complicated diagram, but it shows you one thing. It's a classification of different categories of UAVs, have a tactical and a strategic. For all the civilians application, we are here in a macro, mini, and a bit of a close range and short range. There's a couple of UAVs here. You see people for scales of these are close and short range UAVs. There's more designed for military applications. They like to get into the civilian application. They are complex and expensive machine to operate. It's not really your solutions. At the bottom, you've seen one that is very famous in the mining industry. It's a SenseFly machine, the EB. And you have, of course, the family of the DJI machine, which is the one I show that is very mainly used now in geophysics. And, basically, in terms of UAV application, we're more in a macro and a mini range. Basically, a machine that has less or up to an hour endurance and is less than 10 kilometer range, and with a takeoff payload weight of the weight of 5 to 10 or 15 kilos. And that's the kind of machine you use. Now, you've seen that most of the UAVs are rotary machine. There is a couple of fixed wing machine. In terms of geophysics, the fixed wing machine is a bit of a problem, is less efficient, and particularly because integrating a payload into those machines means completely destabilizing the aerodynamic. So it means it will be faster to build a new machine for the specific payload you have. And also, obviously, most of the fixed-wing aircraft will need a launch catapult or something like that, or still will need an airfield. Now, it's not really effective for UAV. So your vertical takeoff and landing, the VTOL is a term you will hear or see frequently in the industry, is basically the best platform to carry the tools. Let's move on to a couple of geophysics slides now. In magnetics, you'll have at least, well, we have a dichotomy of type of platform. You'll have here on the left, the drone mag system from Genesis, a manufacturer in Canada with an hexacopter, and it's used here as a bird, as we call it, because then it uses a specific sensor, what is called a cesium sensor, that is highly sensitive to noise, so we try to keep it away from the rotor. And then you have the approach Earth we used in fact the flux gate magnetic sensors, and then we can mount it here just below the drone. There's a small boom here, which once in the air will be deployed vertically to stay a little bit away from the rotor. And you have the same here with one sensor on either side for gradiometric. And so what you have is two approach, and I'm gonna go through it on the next slides. On this table, you have basically a couple of technical specification of flux gate magnetic sensors here, and here the cesium sensor. So the cesium is basically the traditional sensors that have been used in airborne geophysics for a long time. It is a better sensibility and a better accuracy, and we're talking about numbers here is basically lab bench testing compared to the flux gate. Now, what is interesting is that any cesium sensors, magnetic sensors used in airborne industry will always be used concomitantly to flux gate sensors, because you use a flux gate sensor to correct and calibrate the cesium sensors. And but the advantage of the FreshGate sensors, it's look at the weight, it's nothing compared to the kilo for cesium sensors. And that has been a reason for us to first focus on the FreshGate sensors, and it's why you have now more and more FreshGate magnetic sensors appearing on UAVs. At the bottom, you have a diagram where on the right you have basically a curve on nanotesla, a profile, sorry, of nanotesla measurements of the cesium from a geometric system. And the same here measured with a Bartington. So you see a lot of noise, but the advantage of a Bartington is that it's pure raw data. There is no filtering on that. On the cesium sensors, there's always some fiddling with the data somewhere along the line. And that's very important to have from my perspective, but can have always discussions with geophysicists to have the pure raw data from the FreshGate sensors. Let me show you some work now. That was a survey done in Western Australia. You have typical bush, and that was one of a quadcopter. The sensor is just on the other side on this horizontal boom, and it will be deployed. What you have here is basically okay, well, that survey was done or was attempted 2 or 3 years ago, and we deployed pilots with thousands of hours of UAVs, but we had to use a local pilot to fly from a service company that was also offering the REOC, and basically that pilot couldn't cope. That's as simple as that. So the survey was rather a fiasco. We couldn't do it properly, but while there, we did a test to compare what a UAV mag can do against ground data. So you have here that on the left-hand side diagram, you have the ground magnetic data, and on the right-hand side, you have the UAV-borne magnetic data was acquired at 15 meters above the ground and with 20-meter line spacing, only one sensor. With a total magnetic field map, all at the same scale. In the middle, you have basically the ground data upward continued to 15 meters above the ground to allow for a comparison between the UAV and the ground mag data. And you can basically see very similar map showing similar main structures. And that's an advantage is you obviously have a lot of more higher frequency signal from the ground data, but in that case that the mining company was quite interested to see what could be done a little bit higher than the ground to clear or to stay away from most of our high frequency noise, which is not necessarily interesting for in some prospect. And still 10 meters below what an helicopter would do at 25 meters above the ground. Another advantage of the FreshGate magnetic sensors, and that wasn't done on a UAV, but that was done on one of the small aircraft, but it's with the exact same magnetic sensors, is that the FreshGate magnetic sensors measure the vectors. They measure the free fields, there's north, south, east, west, and a vertical component of a magnetic field. Now, if you're capable of putting an inertial navigation system that can reposition in space the free vectors of the FreshGate, then you're capable of doing vector measurements. We have here a first attempt, very noisy, which we did on a manned aircraft. It's possible to do on a UAV. It's just that you need to have on board an inertial navigation system, and that's development works. It hasn't really pushed so far. It will be very important in terms of magnetic exploration when you are at the equator, where we have a lot of problem with full field magnetic measurements. But that's something coming. Something else that we're pushing us is basically, instead of using the normal quadcopters, small DJI machine, which is very famous now in the public also, you have here the Mavic DJI, which certainly people and some of the listeners must be using on a weekend. That machine hold in your hands with the arms can be folded back. And what we did, we installed the magnetic sensors below it. And what you see here is basically the first map. On the right, it's a ground mag. So you have roughly from the red to the blue, you have 100 nanotesla roughly of a TMI map here. And here, superimposed, we have the map that was acquired with that DJI Mavic. Now, that project is something we developed in-house. The idea was to develop the idea is to develop a rucksack UAV-borne magnetic system, which ultimately will be completely automatic. What we are now doing is a lot of software developments, and we try to put all of that in our R&D projects, which we might eventually develop with Meriwa in Western Australia. But the idea is to basically have an automatic QA/QC of all the data, and all of that fed back into the software, the management software of the UAV, which can plan the next reflight automatically, and also some in-field magnetic maps, and including also targeting anomalies. The idea is to shortcut the time between the acquisition and the decision you can do on a map for a geologist, particularly if he wants to go and check specific anomalies while he's already in the field, instead of coming back to the office and having to come back again in the field. So that's a project that is ongoing, and we will hopefully can push over the next 6 to 8 months. UAV Gamma, it's there. And that was a project about 7 years ago. We had a big two-stroke UAV, 60,000 euros, not mature at the time, lots of headache, but it was there. It was a big machine. We just put a handheld gamma spectrometer below it and went to fly here in South Africa over an old abandoned gold and uranium mine, which was an environmental disaster. And quickly we saw that each time we were entering or getting out, or entering or getting out of the dump, we had this spike of uranium, potassium, and thorium here. We never pushed that further for various reasons, and basically that was the early days for us with the UAV, and we were struggling enough with that technology to make it work. But today you have a producer, a manufacturer of that is called Medusa, a system we use on our small aircraft. They have the MS-1000, which is a 6.2 kilos, and it's why I said earlier, is Gamma UAV ready? Yes, it's there. It still needs a UAV that can carry 7 to 7.5 kilos with everything together, and it's not a cheap $2,000 or $3,000 UAV. It's still something at $15,000 plus the system itself. So you're talking about 60 to 70,000 euros to fly there, but the technology is there. It exists, and I show you some results that was produced by Medusa. The reference is here for that report. On the top, you have potassium, then thorium, and then uranium. On the left each time, you have the UAV results, and on the right, you have the ground surveys done with an MS-2000, a different system, but the data on the ground was resamples to the exact position of the UAV mapping. And you can see that for each of the 3 parameters, uranium, thorium, and potassium, you have very similar distributions. Here on potassium for the ground, you have a much higher concentration than what was measured on the ground. It might be just due to the ground conditions here that a survey in Netherlands. On the uranium, you see a lot of more bullseye situations, and that might be due more from the data processing itself. But in comparison, you can see that UAV Gamma, it's pretty much here. And that survey was flown at 10 meters above the ground. Now, that's a big challenge in Gamma. The higher you fly, the bigger the system you need. You need a bigger crystal, so the further away you are from the ground, you lose resolution. And obviously, at 10 meters or 15 meters above the ground, you need to go towards more a MS-2000, so which means you go towards a 12 kilos. So that's a bit of a challenge with gamma spectrometric, but the technology is there. Electromagnetics. So right now, what you have here, it's a system produced by GeoFX in the States. They have here the UAV version. It's basically a modification or an upgrade of the ground equipments for measuring conductivity. What is interesting on a GeoFX system is that it has a programmable frequencies, so that you can modify basically before surveys the frequency depending on how much what depth you want to go and what you are targeting. The tool was developed for subsurface imaging, 10 meters below ground level. It's a 3 kilos system, and as you can see on the photos coming from a website of a manufacturer, it has been mounted on a skid of a UAV. So it's no longer us, what we started years ago. It was we tried to use the ground equipment and hook it up with a cable under the drone and then try to fly as a bird. Now, I have seen data, but they're still confidential. This is very promising, but the development is still ongoing from the manufacturer, but it means that soon UAV electromagnetics might be available also. Now it's a subsurface exploration tool. So it might be very interesting for brownfield exploration projects, in fact, and close to the mine. Gravity, well, it might become a reality. Let's look at what is a gravimeter. Right now, from the ground to the airborne, you're talking about 10 to 75 kilos. And obviously, as soon as you're in airborne, anyway, 75 kilos is the lightest equipment system available, and it's $100,000 to $70,000. Now, an alternative to a traditional gravimeter system is to use accelerometer, but they're usually not stable, if that's what you have in your cell phone. Now, they're not stable enough. And the University of Glasgow has basically worked the past few years on what they call a Ouija, which was an enhanced smartphone accelerometers, and they manage to measure repeatedly the Earth tide. So actually, we might, from them, have basically this first transition from an accelerometer to a gravimeter. That's some photos of a design. That might be still 5 or 10 years away from us. In the meantime, from a normal 150 to 75 kilo gravimeter, traditional gravimeters, you have now a system called a strap down system. They are 30, 35 kilos and they have a size of 2 big shoe boxes. Will that be the first available gravimeter for the UAV? Well, maybe, but gravity is not yet there, but there's works ongoing. A couple of aspects on a UAV and collision. Now, there's 4 ways to basically avoid collision of a UAV flying. First, something that was developed by Flyability in Switzerland. They basically they were looking for collision. They designed a UAV, we put an exoskeleton, and it wants to bounce into things, so it can bounce back and carry on exploring. And then you see it here going into places. So that's basically not going to be useful in exploration because the exoskeleton will get stuck into the branch and everything. But that's one approach. Obviously, the exoskeleton is an extra weight on our UAVs. The second one is anti-collision sensors. With some of DJI UAVs have some sensors already. They are working. Us, we managed to stop a UAV flying at 50 centimeters above the ground in front of a fence or even tall grass, but you have to fly very slow. So the anti-collision sensors are not yet there, but they're gonna come. Then the other solution is to fly from a digital surface model, which you will have to acquire from a LiDAR. Now, obviously, this means to do the survey twice. You have to fly once with photo or with a LiDAR, get your surface model, and then set up the automatic flying of your UAV based not on a SRTM, but on a digital surface model. And the last option, which is the one used right now, well, then you need a pilot. And he has to permanently keep an eye on basically the return of the video from a UAV so that it doesn't hit a tree. And these are a couple of challenges. We'll have to see what it goes to make a flyer easier. And what is the future? And something that is developing, not in the exploration yet, but it's, look, we are moving to a world where the drone will operate entirely on their own. We see that already in mining industries. Some operations in Pilbara are controlled from Perth, from the trucks or the train. And that's going to happen the same way for drones. We'll have to remove the UAV or the octopus, get back to my story. But in other words, we have to take off, carry out the missions and land completely autonomously. And that obviously will need a communication management software that coordinates all of those missions and pilots the aircraft instead of a human. And that has to be done without any operators on the ground or in the air. Obviously, everything has to be pre-scheduled missions. And you have already two companies here that provide or design some system. What you call here is what we call a nest, into which the drone can land and take off automatically. Is also charging once it's on a nest, and that's a software interface. That company has moved a little bit further, where they put a nest that's a foldable arm that gets in and out with the UAV so that it can take off and land, and that's on top of a car. That is existing already. We also busy with feasibility study, talking to this company just to see what can we first put a mag on it and see if it's workable. But this is coming. And well, basically that's my story.